Right, so we're now starting chapter 3, right? So we've kind of talked about just, chapter 1 was just an introduction to some things, right? Chapter 2 kind of helped us learn how to visualize data, helped us learn how to describe different types of studies, right? Yeah, so now notice we haven't done a ton of, we calculated the class width, but we haven't really done much about how to describe our data. So this section has some other things in it too, but we're talking about, right, when I have a data, right, you can, if you have a few pieces of data, right, you can just publish all of them, but that's too much, right? Remember we looked at that, even with a few pieces of data, right? We looked at those times of how long people were waiting in the drive-through line to get their McDonald's or whatever it was, right? There's too much data there to just look at it in class and get an idea of what's going on. So one thing we thought about is we can put in a histogram. The other thing, and then we talked about like the shape that the data made. Was it normal? Was it skewed? Was it uniform, right? So here we're going to talk about where is the data, right? So if you have, imagine a histogram, right? You kind of have two things. Where is that histogram? Where is its center? And then how spread out is the data? And in what sort of pattern is it spread out? So that's kind of what we're going to focus on today. So a lot of this stuff, the nice part is a lot of what we're doing today, but we're just kind of pinning it down. And hopefully you have your calculator with you today, because I'm going to show you how to start doing things on your calculator. If you don't, that's okay. You can watch this later. But you need to have you need a graphing calculator, or you can download one onto your phone, but you at least need to be able to borrow a graphing calculator on the days we have assessments. Okay, so we're going to describe some measures of center. We're going to talk about what measures are outlier resistant, which means we have to tell you what an outlier is. We'll learn some of the 3 measures of center that you hear the most, which you've probably already heard. Has anyone heard mean, mode, and median before? Right, so we'll just do that. We'll talk about a weighted mean. Has anyone ever heard the phrase weighted mean or weighted average? Okay, so we'll talk about how to do that, and we'll use technology to do some of these things as well, right? So again, I talked about this before, right? So there are 2 types of statistics, right? Descriptive statistics is kind of boring, right? And unfortunately, we just kind of have to go through this, right? Which is what we start with. Descriptive statistics is I collect a sample. I have some data. How can I describe it? It's right in there, right? Where is its center, right? How much is it varied, right? That's not particularly interesting because, I don't know, it doesn't allow you to predict the future or make any conclusions unless you have access to all of the data, right? We would like to know what the mean height of an American is without actually measuring the mean height of all Americans, right? We want to do it from a sample. So that's inferential statistics, right? That's what the second half of this class is about. This is the stuff that's actually exciting. This is what statisticians do in the real life, but these are the tools. So we need to start here, right? Descriptive statistics, you will not be making inferences about anything. You will just be describing data that you have, right? If you have 800 pieces of data, right, you don't want to list all of them. That'll take a long time, right? You want to describe the set to somebody in a way that's more convenient than that. We get the difference between descriptive and inferential statistics, right? So the New Hampshire primary was done yesterday, right? And they're probably still telling some of the results, right? But descriptive statistics is just, okay, they actually have all the votes now, right? So they can give you, so that's just describing those, right? Then inferential statistics could use information, right? It's like polling data, right? You poll and you say, this is how many people I think are voting for Nikki Haley. This is how many I think are voting for Donald Trump. And like, this is my measurement of uncertainty. This is what I'm using a small number to infer something about the whole population. That's later, that's more interesting, right? Because it can predict the future. but we're not there yet. A measure of center, right? This is kind of one of these things that's kind of circular. You just kind of have to know what it means. It's a measurement, right? You have some data values. They're not all the same number most of the time, right? If they were, it would be very easy. You could just say, I have 800 pieces of data, and each of them is 30, right? But assuming that they're not all the same, you want to talk about where the center of that data is. And then there's not one definition of the center. There are different definitions, and some of them are more useful than the other one, right? So the mean, or technically arithmetic mean, there's something called a geometric mean, but we won't use that in this class. So that's why there is the term arithmetic before it. But in this class, we will just call that the mean, okay? But if you see the word arithmetic, that's where it comes from. All right, and it's very simple. You measure, you add up all the data values, and you divide by the total number of data values. I'm sure you've all done this before, right? So the mean is fairly easy to calculate, but it has some advantages and disadvantages. So I haven't toned the number. So this is something that we'll learn about later, right? We're not doing inferential statistics, but it's good for us to know a little bit about inferential statistics to understand what sort of descriptive statistics are the most useful, right? Sample means drawn from the same population tend to vary less than other measures of center, right? So that means that if I'm randomly selecting groups of 30 students, right, from all of SXU, and I look at their mean height, those would be less spread out than if I use some of these other measures like the median and the mode, right? So that's nice because you don't, that means that you know it's probably, like if you collect it from a sample, it will probably relate to the population so much. Again, that's getting into inferential statistics a tiny bit, so I don't want us to get worried too much about that. A mean of a data set uses every data value, right? So if you change any value in a data set, just one of them, you by definition will change the mean value, right? So everything contributes to it, right? The median, which we'll talk about later, is the middle, right? You change data without changing the order, it doesn't change things. So there's certain, right? You want the center to be somewhat sensitive to the data, so this is nice. But what's the big disadvantage? A disadvantage is one or several extreme values can change the value of the mean substantially, and then the mean might be no longer representative, right? So just imagine we're in this classroom, right? And let's say the governor comes and visits us, right? All of a sudden, if someone took the mean value of income, because Governor Pritzker is a billionaire, right? He's involved in the Hilton hotels, would say that the mean net worth of people in this class would be about maybe $10 million. Definitely not representative, right? Even if we took the mean now, I mean, I don't know, maybe some of you guys have some own businesses. I imagine, well, income. Yeah, I got a lot of student loans already, so my net worth isn't great either, right? But if we looked at the income, right, even taking the mean income, right, mine would probably skew yours. So it's a good chance that the mean income, right, of students in this room, right, is not a good value. It would probably be higher than almost all of you in here because my income's probably significantly, I hope, is more than all that you're making. Otherwise, I don't know why I'm doing this. Okay, so that's one thing. It is not outlier resistant. So if there's an extreme value or a couple of extreme values, right, it can change things significantly, right? So just resistant just means that how much it changes in the presence of a couple of values that are different than the rest of them, right? Ideally, most of the time, you would not want your data set to, you wouldn't want your measure of center to, the measure of center is supposed to talk about the whole distribution. We don't want it to be affected by just a couple of values, right? So that is a big con of the mean. Any questions on what I mean by resistant to outliers? Okay, so this is just some notation, right? This thing right here is called, this is the uppercase letter for sigma. We don't really have fraternities and sororities here, but if you have a friend who goes to university that does, this is a capital Greek letter, so it's often in the name of fraternities and sororities. But in mathematicians, it means add everything that's next to it, right? So I'll kind of give you an example of that. X represents individual data values. N is the, so notice there's a lowercase and an uppercase n, right? This is just to help us clarify. We'll talk more about this later, but it's just to help us clarify how to do a couple of things, right? So lowercase n, right, is the number if I collect a sample, right? So that's how big my sample is. Uppercase N is how big the population is, right? So if I have a sample, I can calculate the sample mean. So this, X with that horizontal line on top of it, you read that out loud as X bar. That just means the mean of X, right? So what's the formula for it? Well, this means the sum of the X's, right? Each data value being a different X, divided by the number of data values. Obviously, the mean of a population is calculated the same way. You just have to divide by the number of values in the whole population, right? And then you use this symbol right here. It kind of looks like the letter U, but that is the lowercase letter mu, right? So we call this mu. This is another Greek letter, right? You might be wondering why we need different things, right? Can't we just use one symbol, right? Because we'll just know if we're talking about a population, right? The mean symbol would mean the population mean. If we're talking about a sample, it means that. Notice in inferential statistics, we will later have to use, right? Inferential statistics, we're going to use X bar to estimate mu. So we need two different symbols because later we're going to be using the same symbol like in the same problem, in the same story. So you want to use this to be less confusing. But for now, it just means you have to memorize some more things. I think this notation is pretty straightforward, but if there are any questions on anything I've said so far, now would be a great time to ask. Okay, so let's do an example of one. I'm pretty sure this data set is made up, but whatever, right? So beneath is the number of cars owned by the last 15 presidents. I got this notes. This data set's just made up, okay? So notice this is a sample, right? Because there are, I believe, they say Joe Biden's the 46th, but Grover Cleveland served 2 non-consecutive terms. So there are 45 individuals who were presidents. I guess most of the earlier ones probably didn't own any cars, but nonetheless, here's the last 15. So this is a sample. So do we use mu or X bar for a sample? X bar, right. So we're calculating X bar, which is simply the sum of the X's divided by, in this case, uppercase or lowercase n? Lower, right? Because that is the sample size. You can easily see 3, 6, 9, 12, right? It's 15 presidents. So in this case, lowercase n is 15. So all you do to calculate is pretty straightforward. You add them up, you divide by 15. You do this, you get roughly 2.6 cars. Sure, you've all done something like this before. This is nothing new under the sun, right? Hopefully I wrote down all of the data values. Maybe I missed them, but I did this earlier. So you can write this example down, but it's pretty straightforward. Now let me kind of give you an idea of what it means to be outlier resistant. So, I mean, I don't know. I've read that some celebrities, Jay Leno, that might be dating me. I don't know. Probably half of you don't know who he is because no one watches late night TV anymore, right? Jerry Seinfeld, both of you probably know who that is, right? So both of them are multi-millionaires who enjoy collecting cars. And let's say, I don't know how, but one of them becomes elected president, and that individual, let's say the next president owns 100 cars. Not common, but it's possible, right? There are people who do that. Well, let's consider that for a second. Let me change the color there, actually, just so we can see this. So that would change the sum from 39 to 139, right? It would change the number of presidents in the sample from 15 to 16. You plug that in, you get 8.7 cars. That 8.7 is more cars than every president except for the one with 100, right? So this is what I mean, that the outlier, that a mean is not at all outlier resistant. It can be easily affected by a single outlier piece of data, right? And then the mean isn't very representative all of a sudden, right? So if you're ever interested, right, there are other things we'll learn about the median. It's much more resistant. For certain types of things, they usually talk about mean. And other things they talk about median because the outlier resistance. For, example of home values, incomes, since there are some very wealthy and very expensive homes, right? They typically want to use the median because the mean is typically too high. It's not very representative. We kind of get what I mean, that the mean in certain, when there's outliers, is not representative of the data. Okay. Just some caution on terminology. We should not use the word, and I might accidentally do this a couple times because I am not a statistician by training. I'm a mathematician, but I know enough statistics to teach, this class. You should not use the word average because the word average can be ambiguous mathematically. So you will never see the term in anything. The word average is typically not used by statisticians or in any professional journals, right? If you're all studying business, maybe you become a business scholar of some kind. If you write something in a business journal, anything that's a professional journal, even if it's not used by statisticians, should not use the word average, because average just means a measure of center, and these are all things that are measure of center. You can use the word average. I might occasionally use the word average, but I'll be using it as a verb as opposed to a noun, if you understand. So you should not use the word average as a noun. I might catch myself doing it because average, while we use it in everyday conversation to mean the mean, it can actually mean any measure of center, which is confusing. Questions? Moral of the story, you don't have to write all this down, right? And again, just try to summarize. You have all the slides online. Summary, the moral of the story is don't use the word average because it's not clear exactly what you're referring to. Okay. Anyone can tell me, like, I don't need a form, like roughly what a median is? It's the number that's in the middle. That's exactly what it is, right? So it is the middle value when data is arranged in order. It doesn't, I guess since it's the middle, it doesn't matter if it's increasing or decreasing. Yep, these are all measures of center, right? Because you can think of it, you could think of right? That's what this whole section's on, right? So the mean has some disadvantages, is that like it's not calculated by it has other problems, right? It's not as rigorous mathematically, but it is very resistant to outliers, right? So if I add an outlier, right, to a piece of data, it just moves, like if it's a number much larger, it just moves the median one space over in the middle, which is not as much as there, right? So if I have a set of data, right, if I change the maximum value from 100 to 10,000, it's not going to change the median, right? Because it's the middle value still won't change. So summary of this: median is middle, it's outlier resistant. So we're typically, we don't use a variable to represent it as much, so I wouldn't worry about this. N with a little squiggly line, which is called a tilde, right? Those of you learning foreign languages might have the symbol. It's used in certain foreign languages, right? So X tilde or capital M or MED, those are all abbreviations for the median. The procedure is pretty straightforward. To find the median, you need to really have the data listed in order, right? So that's something that can be inconvenient. If there's an odd number of pieces of data, right? Let's suppose you have 15 pieces of data, right? Then the seventh piece of data will have, the eighth data will have 7 pieces of data to the left and 7 to the right, correct? Now, if you have an even number of data pieces, even number of values, there is not one value that's in the middle, right? Think about it, right? If you have 4 pieces of data, the second, right, the second value has 1 to the left, 2 to the right. The third value has 2 to the left, 1 to the right. You can't really get around that problem. So for the median, if it's an even number, you take the mean of the 2 middle numbers, right? So if you have x1, so let's say these are ordered, the median, you would add x2 to x3, and you would divide it by 2 in case of an even number of pieces of data. A lot of you probably know that. Already, but that's just something in case you had forgotten it. Questions on how we calculate the median. So sometimes the data might not be ordered. What you can do is you can either put the data in order, calculate the median, or if you'd rather not write that much, you can kind of cross off or mark pieces of data until you get to the middle. So let's do that for number 2. So what is the minimum of the first data set? The smallest value is, that's the second one. It's example 2. Okay, so the smallest one is 12. And so I cross off, so to kind of move to the middle, I need to cross off the smallest and the largest, which is 32, right? And then I do that with the remaining pieces of data. So now the smallest remaining is 14. The largest remaining is 25, right? And then the smallest remaining is 18. The largest remaining is 21. I had an odd number of data pieces, so there is one thing left in the middle. So here the median, so I could call that x tilde if I want, is 20. And we can do for the other one, 0, 13, 2, 11, 4, 9. But now notice, following this procedure, right, I'm left with 2 pieces of data because it's an even number of, so then I just add these 2 together and divide by 2, right? So that gets me 13, which of course is 6.5, or let's use decimals here, 6.5, right? I think you've probably seen a lot of this before, right? So that's just a procedure. So that's mean, median. What's another measure of center that we've learned? Or we haven't learned, but you've probably learned at some point in your life. Another M. Mode, which is simply the most frequent data. So the mode has a lot of disadvantages. One, there, depending on the accuracy, if you're measuring something that is a continuous variable, there might be no mode, right? There could be multiple modes. And while we, it's only in the center if you have a distribution that's kind of normal, right? So it has a lot of disadvantages. So we don't use it that much. We don't use mode much. But let's just define mode, right? So one advantage is it can be found with qualitative data, right? So let's say I get people's favorite colors: green, yellow, blue, blue, green, green. Well, this is 6 individuals. This data set has no numerical values. And for the small celebration, this means favorite color is what level of measurement? Interval, nominal, ratio, ordinal, nominal, right? So for nominal data, you don't have an average, right? Like, I don't know what the hell green plus yellow plus blue divided by 3 is, right? So there's no meaningful way to order these, right? So there's no median, but there is a mode. What's the mode of this data set? Green. Those are G's. I'm sorry if you can't. It's okay. You'll get used to my handwriting, right? This is good. I didn't need to put my name on really anything. I turned into my teacher when I was a student myself. I did, but it might have distinctive and difficult to read handwriting. But do we get the idea that green here is the mode? So if you have nominal data, the mode is the best thing you can do as far as a measure of center. Now, if 2 data values occur with the same greatest frequency, right? So for example, if I had a data set like 1, 2, 2, 3, 4, 4, well, 2 and 4 both occur twice, both have equal claim to being the most frequent piece of data. You can't really make a distinction between choosing them. So you would just say this thing has 2 modes, which are 2 and 4. So a data set that has 2 modes is bimodal. If it has more than 2 modes, it's called multimodal. Now notice from this definition, if I gave you the data set, let's say this last sentence weren't here, you would have to say, well, everything occurs once. So every piece of data is the mode. So 1, 2, 3, 4, and 5 are all the mode. That's just kind of silly, right? So we would just say that this has no mode because nothing repeats, right? So I know I'm kind of blowing through some of these pretty quickly, so please slow me down if they're not, but nothing here is groundbreaking, right? So in this case, looks like I got 1, 2, 3, 4, 5 ones, and nothing else occurs that often. So the mode for this first data set the mode is 5. Or B, what is the or the mode or modes? 2, but what else is in there 3 times? So in this case, this is called bimodal, right? So it has the modes 2 and 6, right? You can definitely see this is not necessarily an advantage of center, because which one's the center? Those are, I mean, 2 and 6 aren't very different for certain things, but for this data set, that's a big difference, right? And then this final data set, what would we say about that one is regarding the mode? No mode. That's one of the biggest disadvantages of the mode is like if you want to use it for center, you kind of need one. So that's a problem. Yeah, question. Why did I write 5? I think because it occurred in there 5 times. I did that to see if you were paying attention. No, that was just, no, I've been known to do stuff like that. So if you see that, you're probably not crazy. I probably just did something where I'm very good at, math, but still with my dyslexia, with my writing, sometimes I can easily, I was thinking, I can think to myself, the number 1 occurs 5 times and easily write the wrong number in my head. So just please let me know if I'm doing that. All right, so those are the 3 you've probably heard of. This one you probably haven't heard of, and it's not particularly useful because it doesn't really mean a ton. One you could say the mid-range. It seems like the mode because it's the number that's in the middle of the minimum and the maximum. Or is it? Okay, I have to take attendance, so this is a good time for you to leave a discussion question. This is the middle piece of data, and right? You could say this is the middle because it's the minimum plus the maximum divided by 2. How is this the same thing as the median? Is it different? Is it usually the same, but sometimes different? Just talk about, first determine whether this is the same thing as the median or is it different? And if it's different, how is it different, right? So just quickly turn and talk to the people around you to see if you can get to the bottom of that. Okay, questions. Is this the same or different than the median? It's different, right? It can be confusing because you might both think of them as being the middle, right? But it's a different type of middle, right? So for example, if I had the data set 1, 2, 3, 4, 20, the median, this is the median, right? So the median is in the middle of the data sets, right? The mid-range is in the middle of the range as like a number line sense, right? So it'd be 1 plus 20 over 1, 10 and a half. Yeah, it's kind of like a midpoint, right? It's the midpoint if you put like but notice the midpoint, the mid-range isn't used very much because it's kind of terrible. Is it at all outlier resistant? No, and it doesn't and all like one, it doesn't depend on any but 2 of the pieces of data, right? So it really represents the 2 endpoints. That's it, right? So I guess it has 3 redeeming features. It's easy to compute, I guess, right? It can reinforce that there are important pieces of, there are several ways to define the center of the data set. It's also incorrectly confused for the median, so it helps you think about the difference between the median and the mid-range, right? So that's about it. Again, we can just see that it's very easy. to calculate, right? So the mid-range here, you just add the minimum, which is to the maximum, everybody, which is, and you just divide that over 2. Notice it's terrible on outlier resistance. Add in 100. You get 50 cars, which is even worse than 8.7, right? So yeah, mid-range is just terrible. It's not really, I don't know if we're ever going to use it again in this class, like after this chapter, but they mention it. Oh, I can't really think. It's mostly just illustrative, right? It's just a way to describe. Yeah, it's mostly just an illustrative to say you could come up with multiple ways to find the center. If I thought for maybe 20 minutes, I could come up with an example where maybe that is, but I can't really think why that. Like, I guess if you have different destinations, yeah, I don't know. I don't know exactly what you would use it for. There could be something. I have to get into it. So these all have been short sets of data, right? So I want to show you how to use your calculator because it's particularly useful, right? And it gives you a lot of pieces of information. So you don't really need it to use it on any of these things, right? Because it's pretty easy to calculate by hand. But if you have your graphing calculator out, you have one with you, please bring it, get it. And I will show you a little bit of how to use it. All right, guys. So we could easily do this by hand, right? But I'm going to show you how to use your calculator just for illustrative purposes. I could probably get some program, but I've never had. Okay, so last thing is a weighted mean, right? So when different values are assigned different weights, you can calculate a weighted mean by using this formula where W is the weights, right? So you can think about this like imagine mixing solutions, right? If I mix two solutions, one of which is, I don't know, 5% juice, the other one's 10% juice, right? The mixture will only be exactly 7.5% juice if I mix equal amounts of both, right? So for example, let's say I have 10 ounces of something that's 80% juice. And 2 ounces of 10% juice. I don't know. I'm just making this up. You can then use these as weights, right? So the percentages, the number of ounces are kind of the weight. So it's 10 times 80 plus 2 times 10, right? Divided by 12, right? So the weights are 10 and 2, and their sum is 12, right? So that's the calculation you would do. So here's an example of where this is happening, right? Like you might have a class that each midterm is worth a certain percentage of your grade, but the final is worth a larger percentage, right? So here's an example of this, right? So find the mean, right, if the last test is worth more than the other four. So the first four tests each have a weight of 15. Then the sum of the weights would be 15 plus 15 plus 15 plus 15 plus 40, which since it's a percentage ends up being 100%, but there's no rule that the weights need to add up to 100. Generally speaking, you plug that in your calculator, that will give you the weighted average, which is 79.3. Now, the weights don't matter if you scale them as long as you scale consistently. So perhaps you would say, well, 15%, that's really a decimal of 0.15, right? As long as you change them consistently, it will still end up giving you the right answer, right? So if you double, so like if you divide all the weights by 100, the sum would also be divided by 100, so the two effects cancel each other out. So you can scale it either way, it doesn't matter. Yeah. Just the weights, the weight of each thing. So the weights in this case are what percentage of the grade it's worth. It just kind of depends on, you have to kind of figure out by the context. So here, right, like one test is 40%, the other tests are 15, right? So those are the weights. In this juice example, the weights are how many ounces, right? You want the 80% juice to be 5 times as important as the other one, since there's 5 times as much as, if that makes sense. Any final questions? Okay, so let's do the small celebration now.